Okay, so I'm going to go over the last little bit of the factoring algorithm that I neglected to finish yesterday, and then we're just going to like go ahead and try and sort out problems from the project, knowing two things, right? I'm not Yanni, so I can't answer any questions about what should we do here, like what are we going to get marks for or not. I'm not privy to those conversations, not being the coordinator, and wouldn't even say intermediate Julia programmer. I'm an okay Julia programmer, so I'm going to try to help you the hardest that I can. Certainly anything about the algorithms I can be quite helpful with. All right, so let's just go here. So let's just remember what we did yesterday, and that was I finally went over the algorithm for factoring univariate polynomials over Zx. And how did we do that? It was a multi-step procedure where the first thing that we did with the polynomial was make it square free. Remember, a polynomial is square free when it doesn't have any repeated factors. And I'm saying if we take the original problem and clean it a little bit, we're left with a simpler problem to solve. That's enough of the solution to the factoring problem. Remember, I said if we factored 12 into 2 times 3, that's kind of okay, because recovering the degrees of those primes is going to be fairly straightforward by trial divisions. Okay, so in order to do a square-free factorization, what we need to do is it here. I'll just remind you that to write f as a square-free factorization is to do this, where each fk is a grouping of all of the roots that repeat k many times, right? So this is the product of all roots that repeat once. I'm not saying that these are all linear. I'm saying these are all roots that repeat once. These are all roots that repeat twice, 3 times, 4 times, and so on. And then we got this amazing property that the GCD of A and A prime, if A has this square-free factorization, is this polynomial, which is effectively A with all of the powers reduced by 1, and in particular, F1 disappears. Well, why is that useful? Well, if I take the GCD of A and A prime and I divide out by A, what we get left is a square-free version of A, right? So this is like taking 12 and reducing it to 6 and then factoring 6 and then going back and factoring 12. Right, so this is a simplification part, like this is sort of data cleaning part of the factoring algorithm. So we're only now concerned about, like, we don't have to worry about repeated roots while factoring. Okay, so that was the first step of our factoring algorithm. The other things that we have to do to simplify it is just make sure that the polynomial hasn't been polluted at all. Right? That is, it's not holding any type of scaling factor. Right, so we can remove the scaling factor by removing the content of the polynomial. Remember, the content is the GCD of all of the coefficients. So if we remove that, then what remains is going to be called a primitive polynomial. So a primitive polynomial is not scaled in any way. And then after we make it primitive, we divide out by its leading coefficient, right? Just to have a monic polynomial left over. Because if we factor something that has a unit leading coefficient, the factors are also going to have unit leading coefficients. That also simplifies the factoring problem. Now, how do we recover in the end that coefficient? Well, we just remember it, right? If we're trying to factor 2x plus 2, we remove the 2 and we just say 2 is one of the factors of the factoring. We're going to get 2 and x plus 1 after that. Okay, so now we're going to start factoring in ZP, and initially we're going to be given a polynomial which is square-free, monic, and primitive. So it's been cleaned in all of these various ways. So it's just the product of distinct irreducible factors. So what do we do then? I said we came up with this really neat idea, whereas if we could somehow take our polynomial and take the GCD of the product of all linear factors, what that GCD would return would be a grouping of all of the linear factors. And then we could take that and we could take the GCD against half of the product of all linear factors and hope to get lucky and repeat this process until what's left is a single linear factor. And I said this idea actually extends to all quadratics, all cubics, all quartics, all syntix, and so on and so forth. And then we discussed exactly, well, how do we get this product without actually explicitly producing that product? And the answer was to use Fermat's little theorem. Where was it? Right, so Fermat's little theorem says that when you're working in a field of prime characteristic, that any element from that field taken to the power of p is the same element, right? So a to the power of p is congruent to a mod p. And in particular, a to the power of p minus a is congruent to 0 mod p. And the reason we want that is so we can form this polynomial. I think it's called a cyclotonic polynomial, or it's close to what we call a cyclotonic polynomial, which is x to the power of p minus x. Now, what's special about this is that if you evaluate x to the p minus x at any integer from zp, it's going to be 0, right? So f of p is 0 if and only if x minus p divides x, right? That is, a polynomial is only 0 if you found one of its roots. Therefore, okay, so x minus a divides f for every a, which means x minus a is a factor of f for every a, and consequently, x to the p minus x mod p is the product of all linear factors. And furthermore, x to the power of p to the power of k minus x is the product of all irreducible polynomials of degree d that divides k. Or another way of saying this, this is going to be the product of all polynomials of degree k, right? But some polynomials of degree k can actually be factored, right? Like, so if I say I produce all the cubics, some of those cubics are actually linear factors multiplied by quadratics. But that's not a problem, right? Because we always know all the linears are given by this. And all the linears and quadratics are given by this. So if we just divide out all the linears, all we're left with is irreducible quadratics. And the same is true for cubics. So that was the general idea. Right. So now what this distinct degree factorization allows us to do is, given our square-free monic primitive polynomial, we now can break that into groups, right? Where each group are the product of irreducible linear factors and the product of irreducible quadratic factors and cubics and quartics and so on and so forth. Let's see if I can actually run that. Okay, so my claim is that our project can do this. So let's see what happens if I run this. X not fun. I have to go all the way up. Or actually, maybe I don't. Let's see. Where is it? Wish there were some better ways of navigating this. I think I just have to say x is equal to x poly. Okay, let's go all the way up. I don't want to because there's a lot of stuff happening again. Okay, I'm not going to fix this. It doesn't matter, guys, because I want to get on to the part where I'm actually helping you guys. We'll read the specification and we can, from that, deduce what's supposed to come out. Where are we? All right, so this distinct degree factorization. So you give me a, right? The degree of a is greater than 0, right? So we're not trying to factor a integer. A is monic, primitive, and square free. This is going to output a sequence of g's, g1, g2 through gm, such that the product of g's is equal to a, and gi is the product of irreducible polynomials of degree I. So it's exactly what I told you the objective would be. And just now we know what this algorithmically is going to look like, where we're going to turn a list of this. So this effectively is just implementing that pseudocode. It's not that important that you understand this, right? Because I don't believe you actually have to engage with the factoring algorithm very much, aside from like updating it to work with the big int data type. All right. So what we have now is a bunch of different polynomials that aren't irreducible, but we do know that what they are products of. They're product of irreducibles of the same degree. Right. So this is why we call this distinct degree splitting. So given a polynomial, which is assured to be the product of irreducible polynomials of equivalent degree, then the following technique factors that, right? And I said, look, all we have to do is repeat the idea that we had for distinct degree splitting, but we choose half of the roots in that case and hope to get lucky. Right, so how do we get half of the roots? Well, we looked at this and we factor out x. We realized that this was the difference of squares. If this is a difference of squares, it factors like this. If this is equal to the product of all linear irreducible polynomials, then surely this is half of them. And the same is going to be true for the higher order ones, because we can do the same type of factoring because the factor of a difference of squares is predictable. All right, so this is going to give you half of all of the roots. Doing x plus alpha to p minus 1 over 2 minus 1 is also going to give you half the roots, but a random permutation of those roots, which is the thing that we need, because we may get unlucky when we choose half of the roots. Remember, the objective is to choose a group of roots so that we're going to be able to factor a little bit the product of all linear factors, for example. And remember, the three options are, okay, so we have G, it's a product of some linear factors. So all of them are either in here, in which case the GCD is going to be G. None of them are in here, in which case the product is going to be 1. Or some of them are in here, in which case we get a proper divisor of G, which means that we factored G into two things, which is a smaller problem, and we just repeat this procedure. Theoretically, if we wanted to work out that this algorithm is going to work most of the time, right, because we can have stochastic algorithms where the outcome is like epsilon, we're going to have to run that quite a bit. We can actually work out that the probability of generating a non-trivial GCD is about 4/9, so close to a half, which is pretty good for a stochastic algorithm. Here is the algorithm for doing so. So this one is going to take in a polynomial, which is monic, and that's assured to be the product of irreducible polynomials of equivalent degree. And we're going to output the splitting of those things. So in this case, G1 through GM are going to be irreducibles of degree D. And so if you give me a cubic and you're telling me that this is the product of all linear factors, what's going to come out of this is 3 linear factors. If you give me something of degree 8 and you're saying this is the product of quadratics, what's going to come out of this is 4 quadratics, or irreducible. Okay, so all that is required now is for us to take all of those ideas and combine them in a way to solve the problem over ZX. And that's sort of what I skipped yesterday. So here's like sort of the pseudocode to work this out like generally. So this is going to be factoring in ZP. Okay, so you give me A, and then what I'm going to output is a list of an irreducible polynomial and how many times it's been repeated. Right, so to factor like x plus 1 squared, you'd get back a list of x plus 1 and 2, right? Because I do want to say like this is P and this is the degree on it, because our computer algebra system has no way of representing x plus 1 squared like factored, right? The internal representation is always going to expand everything. And so this is why we have to present, we can't actually return a factor. We can't return a polynomial back to the user and say that this is the factorization. In Maple, we can, because we have delayed computation. And anyways, so just keep that in mind, right? The factoring algorithm, it's strange because the factoring algorithm is not actually giving you a polynomial back, but there should be a function somewhere in polynomial that helps you, that effectively takes the output of this and like recombines it back into a polynomial. Let's check this. This was... It was like a factoring algorithm. It's a auxiliary function in factor that helps with your testing. Yeah, this one, expand factorization. So if you give expand factorization a factorization, which is a list of lists, this will recombine it, right? For the purposes of like being able to test if you've actually found that factorization. Cool beans. Okay. So what do we want to do? So in comes A, out comes an actual factorization mod P. Okay, take A and duplicate it, I guess. That's what this says. I'm not this is only necessary because I don't want factor to actually destroy what's coming in. We may want to have that style of computer algebra system, like where we are doing in-place changes to things. Spatially, that would be better, but I don't know. Okay, let's not destroy input in this case. So we just duplicate the input. We're going to remove the content of F. That makes it primitive. We're then going to remove the leading coefficient of F. That sort of makes it monic. But we're just going to remember this, right? So you see, I'm just throwing it in as one of the factors in the end. And I'm saying, oh, originally you had a leading coefficient of 2. I erased that and then factored. but in the end, I'm just going to multiply by 2 again. So like, there you go, right? This is not going to make a difference. That's why like only being able to factor monic polynomials was like sort of no big deal in that case. Okay, so now we take this and we take f and we divide by the GCD of f and f prime. That should make it square free. This is the thing that could fail mod p currently, unless you use the better square free algorithm. So technically in this, there should be some statement that's where this can actually throw an error, right? Saying, oh, this is like a degenerate p, I can't actually do this. Let's assume that it's not degenerate and keep going. So the first thing we do is a distinct degree. Oh, I shouldn't have double clicked. A distinct degree factorization. So this is going to give you a sequence of polynomials. All of the roots that are repeated once is D1. All of the roots that are repeated k times are in dk. And then we take those individual things. And I'm saying, oh, do a distinct degree splitting on this product. And I'm telling you that it's a product of univariates. That's what that 1 is for. I'm saying, oh, this is a product of polynomials that are irreducible of degree k. That's what that k is for. Right? So distinct degree splitting needs to be given 2 things: a polynomial, right, and the degree that you expect the irreducibles to be in that grouping, right? So if I was holding like a 4 quadratics that were multiplied together, that would be degree 8. I would give that to just 1 second. Wrong. Always have tea, or preferably coffee when lecturing, and some juice. You guys get a little bit screwed because like my coffee lectures are way better than my tea lectures. But if I drink coffee now, I will never sleep. I will never sleep. And I have children who love waking up with the sun, right? That's what they think. The sun comes up 5:30, great time to get up and sitting in bed, go back to bed. You should all be parents. It's great. Okay, so that's how we factor something over ZP, right? By just going through all of those steps. The final step that I didn't sort of talk about is the easy one, right? So now up at this point in the algorithm, I've said the factorization of 12 is 2 times 3, which is wrong. Okay, so the penultimate thing that we have to do is recover the degree sequence. But this is easy. This is just trial divisions, right? So for each G1 that comes out of here, so each of these G's is going to be an irreducible polynomial, which is guaranteed to be a factor of the thing that we're trying to factor. So for each of these G's, we have to try to remove it from A as many times as we can. So that's what this is doing, right? For each, how did I state this? Because there should be G's in here. How come they're all E's? Maybe the E should be G's. Should they be G's? Yeah, this line is borked. Like polynomial shouldn't even be coming out of. Oh, these are getting the exponents. That's why I called them E's. Okay, something in here should probably be G. Yeah, let's change that. That should be a G. That should be, oh yeah, that even has an M on it. Okay, this makes more sense, right? Because this is an irreducible polynomial that's assured to be a factor of A. And I'm saying, what is the maximum K such that G1 to the power of K divides A, right? So for the 2 times 3 factorization of 12, I want to know the maximum degree on 2, maximum power of 2 that still divides 12. That's 2. Okay, so this is going to recover all of the degrees. And then we just return them, right? So G1 has exponent E1, or G1 is a root that's repeated E1 many times, with the caveat that I'm just throwing back in the original leading coefficient that I removed to make it monic, right? Just so, because if I didn't, then all of our factorizations would be off by a scaling term. And that makes things really hard to check if we're doing it. It's better just to actually give back a polynomial which properly expands to the thing that you were asked to factor. even though I don't care about scaling factors in terms of solving. Okay, so that's the factoring algorithm implemented mod P. Oh, they didn't ask you to do, we don't ask you to do factorization over ZX? I forget, because it changes every year. So there's no Chinese remainder theorem that we've asked you to do for factoring. Okay, so done and dusted. So you only have to do this, right? So probably this should return an error message at some point if we find a bad prime, which you'll deduce from. I guess you don't have to return an error message. It's not technically part of the project, but it's best to. It's best to. Okay, let's just leave that. I don't want to complicate anything. When is the project due? Friday? Okay, so who cares? Okay, so technically speaking, this is a factoring algorithm for ZP that sometimes fails, right? Because I said we can't always do a square free factorization, right? If there are roots that are repeated P many times, because when you take a derivative, they disappear. But I also said, okay, in that setting, I actually know exactly what the square free polynomial looks like in that case, so it doesn't really matter. So you just know that this is going to fail for you sometimes if you get unlucky, but that's fine. It's actually explicitly stated in here. That's the case. So for this factoring one, where does it say? Somewhere in here, it says like your code may fail on small primes, but that's okay. Somewhere in here. Past 7, 6, 7. It's actually not just small primes, right? It's like any prime that would divide a multiplicity of one of your roots. It's just that becomes less likely as the primes become big, right? So you should pick big primes anyways. Oh, here's something I sort of missed. I did watch back the lectures. There's one thing I wanted to mention. So I had 3, 5, 7 in here and then 105. And during the lecture, I'm like, that's strange. If I wanted to add another prime here, I don't know why I wouldn't have picked 11. That's the next prime in this sequence. Moving to 105 was kind of strange. But, pardon me? Is 105 not prime? Oh yeah, it's divisible by 5. So that's strange for a variety of reasons.
Right?
Oh, is that the product of the 3 things beforehand? Okay, that makes...
It's like the minimum thing you need in order to fit all the coefficients.
Yes, I think that's what I was trying to demonstrate, that like, okay, here's the image of that. And then if we take the S mod, we're fine. Okay. Okay, so another observation would be in this Chinese remaindering, you may just find one prime that's sufficiently large, right? Don't start counting from 2. Right? To go the other direction, like pick the first prime that's less than a 64-bit integer, right? Because all like the arithmetic is going to be equally easy in any of those primes. It's all machine arithmetic to the computer, and then you're gonna pass that down much quickly. Now for testing, of course, it's better to choose smaller primes. 101 is my favorite number for this reason. Yeah, and one day I'm going to put it on an exam as a bonus question. Well, because I would have to work with primes a lot in this discipline. And the problem is, if you choose ones that are too small, then funny stuff happens like a lot, right? So I found it, 101 is like the smallest prime that I can choose, which like doesn't trivialize the problem, but is large enough to like show me problems, but it's not so large that the problems are not going to be visible to the human eye. It's also really easy to type. It's also a prime as a binary representation. It's also palindromic and symmetric in all directions, right? So I feel like I have a good reason for my favorite number to be 101. Whereas I asked my 4-year-old, what's your favorite number? It's purple. It's not even a number. No matter how hard I yell at him, he just won't learn math. Right. So that's another thing here, right? If you actually may not have to do iterations of Chinese remainder theorem if you just choose a large enough prime to begin with. Right, so that's capturing your bound. And again, the reason that we have to choose this bound is because remember, we want to solve this over the symmetric mod. So effectively, all we need to do is say, look, I just need enough numbers so that the number field that I'm working in has all of the numbers of the actual product that I'm looking for. Right? So how many numbers do you need? Well, what's the largest coefficient that you have? That's to plus that and minus that is how many that I need. Right? So this is exactly how the height materialized out of this, out of a requirement of saying, look, I need to know how many numbers you have in your coefficient field. What is your largest coefficient? Right. So that hopefully that makes that sort of bound a little bit more easy to understand. And then I felt like because you asked a question about, do we need to multiply by the number of terms? Where was that? Yeah, the hashtag. But there is an example, a real example, which now I can't find. Where did it go? Oh, sorry. I forgot because it's at the very end. Was it? Anyways, in the example, it was clear that if we only multiplied the heights, that was insufficient, right? So I had a counter example actually embedded there. Now I just can't find it. Right. So that's sort of all I wanted to repeat. Is there any questions or clarity that you require for any of this stuff, or just you want me to start roaming and trying to help with the project as much as I can? Sounds good. So no, okay, I'll ask the oh, there is some questions from the. Did we already go over how the prime numbers are selected? No, you just pick them. Just pick them. I'm not sure, Rohan, if you're around, what you mean by that question. Just pick any ones that you want, knowing that the 3 primes 3, 5, 7 from before. Oh, those are just arbitrary, right? Just pick primes and just keep picking them, right, until their product exceeds some bound. But I actually said it's actually better to work in the reverse direction. So what I'd recommend, one of my favorite Maple commands is next prime and prev prime. So given a number, it gives you the next prime after that number, or the prime that comes before, because effectively that's what you need, right? You say, oh, I have a prime. The bound is currently not exceeded. I need another prime. So I'm like, okay, give me the prime previous to this, or the prime after this, right? So that's the only reason I did 3, 5, 7 is that happens to be the sequence of the prime numbers starting after 2. But you could choose them like randomly for all I care. It's everything's still going to work, provided you don't choose one that's bad. Okay, so what I'm going to do, I'm turning up my speaker so that anyone from chats, you need to yell at me in order to come back and attend to you. Otherwise, I'll leave the message on the projector so I can see that as well. And now I'm going to start walking around and trying to help people. That's okay. I did accidentally put the code up for show. So I guess if you guys wanted to lift that, you could take some screenshots or look at the recording, but I assume most of you have done show. But I want everyone in here to try to reverse x cubed minus x and to show me that that works. Actually, yeah, so let me bring back my Jupyter notebook. Because there are some edge cases in there that aren't.
I wasn't able to open it.
Open which?
GitHub, the unit 6.
See, now it's working.
Is it working?
My lord.
Right. But
Okay. So what is that? Okay, so now what I need to do is, what's the flag called? Something like print reverse equals true. Lowest to highest, yeah, something like this. Okay, show me that yours does this.
It says like there's no global variable defined, so there should be something in Julia.
Yeah, technically the language that he uses in the task sheet is do not assume this exists.
Yeah.
So there is a macro what's the macro called again? Yeah, is defined.
And you just put a symbol in,
Yeah, so
or a string. Something
not
like that.
defined. Lowest to highest.
Yeah.
Is defined. So you kind of want something like, if this is defined, and it's true.
Yeah.
Then you need to print backwards. But I'm more concerned that people are accounting for the fact that when you reverse a polynomial, the last thing is not necessarily non-zero. Because in my code, when printing in the usual direction, the leading term is special, right? You don't want to print plus, but the leading term also is guaranteed to exist and be non-zero. So kind of makes that case a little bit easier knowing that it exists. But the same isn't true when you reverse everything. And so, anyways, just run this. Show me that your code does minus x plus x cubed in this setting. And I wish I could have figured out a way to make the Unicode numbers. If I know when I started looking up Julia Unicode kerning that I was going down a rabbit hole that I shouldn't go down.
It's sad that there isn't a constant integer offset between.
That's an assault to my eyes, right? Like that sucks, but this is rather nice actually. But the other thing sucks. I wish we could have it. I don't know how to push them together. I don't know if you've seen my LaTeX style file in math yet. Like I wrote them a custom style file and I said, let's now all standardize all of this mess, right? Onto the same thing. Because I can really go down these typesetting rabbit holes. All right, so just raise your hand if you want, and I'll come around.
Let's do Python against the mods.
Yeah, so how's your
Oh,
adventure in parameterizing everything?
it worked.
Oh, can I
that's
see?
nice.
Yeah.
Because I had some difficulties with some of the inner constructors, like had to be defined in like very peculiar
Yeah,
ways.
it's like new sub T of thing. I just like,
I think it was something in term or like the inner constructor had to like define like an overload to the inner constructor. It was just so weird. It wasn't as straightforward as I was hoping it would be. Yeah, something like this. Yeah, so I was trying to parameterize term by t.
Yeah.
Where t is any integer, because that's
Yeah.
really what we
Yeah.
want. Actually, what we want here, I don't know if Julia can do this. Like, I'm actually getting more interested in programming in Julia. Here, I want to say ring, right?
yeah, yeah.
Or actually, maybe even weaker than ring. Well, at least ring. I'd like to be able to say that, okay, you can take, this can work on any coefficient field, which is a ring. I don't care what it is. That would be the most extensible. Here we want integers. Like, or maybe even number system. You weren't in 3400 with me, were you? No. Okay. So in Haskell, we have a number class, like anything that acts like a number, which is effectively a ring class, right?
You need like Julia to have that predefined because like the type system is like hierarchical. So
yeah,
yeah.
That's not to say we can't go in and say like this is the ring class. Like I'd like to be able to do that.
Then like anyone else who's implemented something which happens to be a ring and they don't know that's a ring, and if you're like trying to use other people's modules, I guess that's not as much of a problem.
Yeah, but we can't not improve the system because of we don't get guaranteed backwards compatibility. It's not going to break any previous code. It's just their previous code won't be. Anyway, it's this what I was concerned about. I don't know why I had to go ahead and like define an inner constructor like this. Like it wasn't working for me until I put that there, and I can't figure out why. Did you have to? That's why I want to come see how you did. Well, what did you parameterize in your code?
I parameterize the same thing.
So you don't have to have that there. What version of Julia are you on?
Check.
I think it's hash. What is this version? What's the flag?
Oh.
Huh?
Expert.
Lowercase version. Need some help?
Oh, I should say that as
Can-
an also did
Yeah.
Parametric?
Parameterization.
Yeah.
I think the way that kind of avoids that kind of shenaniganery is to have an abstract term that takes anything and then have a term be an alias for integer.
Okay,
Yeah, oh yeah, that's what I did.
so there's some hackery that has to happen here, or?
So term is defined to be abstract term of an integer.
Oh,
So term itself has to be abstract.
Well, it's an alias of a concrete version of that.
Okay, have you done this, or?
Yes.
Okay, maybe I can just look at it and now, what kind of connection do you need?
I have a chart.
there are no judging ports.
Yeah.
Yeah,
There's one back there.
there's also one at the front. And like.
I had a fellow in 1001 who, his laptop was old. So he needed to charge it, but the only PowerPoint was at the lectern. So he ran a lead from like like he sat in the front row every time and ran a lead from my lectern to his thing. And I was fine with it. Actually, I'm the one who brought him the lead,
Oh, really?
right? Because it was ridiculous what he was doing before that. It was just like taught between him. And I'm like, you're gonna take someone out, bud. So I'm gonna leave this here and you're gonna use it. I'm not totally happy about this tripping hazard, but
Before you arrive on Mondays, I'm getting my lead from your desk to here.
fine. There should be PowerPoints at all of these things. You gotta pay a hell of a lot of tuition.
That is true, yeah.
And then today I found out what. Cause there's the big topic now is like how many people can actually like stay here in residence. Like housing is a big issue with the government now, like we can only take enough students as we can house. So, I looked at the university I went to, because housing was a guarantee if you're a year one. So we had 6,000 beds at McMaster, a medium-sized school, 6,000. How many beds do you think we have? I just looked this up.
I think it's in the hundreds.
600 beds. Like that is inactive
Or
for
like
huge university.
50,000 students or
The
something.
colleges, I think that can include like the new one. It doesn't count the scapes, which technically are like a private
Yeah.
person, not even.
Like I'm at college, I think we've got like 200. And there's like 7 colleges.
Why do I looked it up? This is like part of the YouTube batch.
Maybe YouTube beds.
But there is one YouTube.
So what was the problem with that you were talking about?
Oh, I had to add this, and I don't know why.
Oh, that's odd.
Yeah,
Yeah.
but I did some digging, and people are like, oh yeah, I gotta add this in. I'm like, okay, why isn't that in the documentation? But like, don't do this. If you haven't already parameterized your code to use abstract types, do not attempt this for Friday. Just forge forward. Just that a little bit of pain at the beginning that helps with you.
That is weird.
No, explicitly on. Is it that if we were to say the best way of doing this would be to make it parameterized? Because if you're literally copy pasting code, you have the same code in multiple places. That's just using different internal
Yeah.
types.
Did like the exact same thing, but I didn't need to use the.
I'm not sure why mine wasn't working.
Yeah, like this is my code, it's basically exactly the same. I've got the same.
Well, maybe it's the fact that I am trying to overload term.
That,
Using
yeah,
number
because
term.
I called mine something different, I shouldn't have.
So I really have to, because I'm trying to I was trying to parameterize in place. like,
Yeah,
taking the
okay.
existing stuff.
Yeah, because I use a type alias for term and big term.
I made it to the constructor, the correct term takes type sheets, and then my term file of them, I don't quite know.
You fix my Chinese remainder theorem code, because that's an alphabet.
My term file is currently 1 line.
So the term for you is just an abstract term, parameterized, what's this zero?
Oh, that's a standard for a module, like not being a modulus.
Oh, I still, actually, that's correct, it's you say,
Yeah.
characteristic of the zero, let's see, it's not adequately consistent.
Yeah,
So then where's your term, oh, it's appreciated.
yeah. So this is what the actual term.
That's your term,
It's messy.
well, abstract. Okay, so maybe what really happens, the fact that I'm.
Yeah.
using
Yes,
term.
yes.
That'll probably be, yeah.
First, I'm sorry.
Yeah, it's a lot nicer to have it, to redefine term being an alias
Yeah.
or something bigger.
Oh yeah, that's the other thing I wanted to mention. So now I'm interested in actually beginning to write the computer algebra engine for Julia. Because right now it hooks into SymPy, and like I've been doing some adventures into SymPy, and we're like, okay, no, let's just nope. Like this should be done in Julia anyways, right? Not it would Julia shouldn't be pointing to some
Typeless.
a Python package called SymPy. For instance, like the first thing I tried to do is say, okay, let's take a look at how it's handling sparse polynomials, like what representation is it using? And my first student who was deployed said, they're not. They have no representation for sparse polynomials. Everything is done dense. And I'm like, that's not possible. Like I was incredulous that they didn't do this basic optimization, but that's the state of it. There's not even, I guess a new student dug deeper and technically, anyway, it's a mess. So if you want to do projects with me, like honors projects, like this is one of the ideas. Like we start building a computer algebra system in Julia, properly developing all of these abstract types, right? So terms can be parameterized by rings. Like there needs to be types for things that are groups and rings and fields. We need to redeploy division so that does pseudo division. So introduce delayed computation to the system. So and a lot of students from this class actually come and do thesis projects with me. I have a relationship with math. Obviously, I'm here, sitting here. They're quite happy to let me supervise students for honors thesis. So that's the first thing. Number two is that I get savaged in the CCATs for this course every year because the project is hard, which I have nothing to do with. I don't set it. Like I just come and give a little discussion about my research area and what I think is a really cool factoring algorithm. I acknowledge that the project that you have to do is kind of tough, but don't at me on that. Like that's not my responsibility. So if those of you who enjoyed these lectures could write me a CCAT to offset the fact that like people are going to savage me in it, like we can at least get me back to something, I don't know, where I don't have to talk with my boss about why the responses are so poor. It really does go a long way. Like you can think of it this way, like if two of you give me fives and one person gives me all ones, right? That like significantly reduces the averages. They're not removing outliers or anything like that. And I'm a teaching focused academic, so this is really my cachet to move forward. So I would appreciate it. So thank you for attending my TED talk and UQ talk, I guess. Okay, more problems in the next. Yes, okay. And help each other. Also, you know that you have access to earlier years GitHubs. Yeah, that's not cheating. Yeah, it's other students' solution to this problem. You can look at it. We don't do a monster like that. Like that being said, like if you cheat, you're cheating yourself. You won't learn anything, but you get really stuff you can lift other people's code. Okay.
So if I'm recording this online, like I did show. I was like, would be pretty looking like that thing. And then my other option and because of it. So like without that one phone, you can see what
So stop trying to. I think it's taken one.
I'm going to partner with the customized confidential project.
Initial.
Yeah. Project zero.
Okay, so take that out. Oh, I see what you're doing. That should also out. Okay. Okay, so is this permanent working or not?
That's which I wrote, which and like this is yes. Yeah. But it's like.
And if you turn it off, it doesn't do that. You show me the code that you're writing. I decided that.
Yeah, I started later, so I just get the lots of bits. I enjoyed it. It would come, but it's back.
I'm right.
Rose. Oh, I'm sick.
Which part of the is hard to understand?
When I was trying to adapt. It's pretty hard. Oh, Oh, so it seems to be reducing more than the.
Well, first of all, don't call her X.
It's not worth.
So that would be the key original of this.
Maybe.
X can't be equal to X squared plus 2X. Then X is one of them.
Because if you look
Like
at
you're
mine,
overridden the X term.
see how I.
We should change that to N.
So that's.
Yeah, this way you better interface. You should be prohibited from.
It is.
I was thinking before actually about places in general. Like if Julia had like a more concrete way of doing thing, there's like other directions, like bringing the deals with maybe better for the interface, because it's like.
This combines every single type. So there's like a lot of structure and general.
We'll sort it out.
Big pictures, not even one here.
Well, we have access to the
Big type,
developers.
they combine sort of.
We can actually shape the development pathway of this language. Turn it into Swedish and Rust.
Yeah, pretty much. Is that the?
Okay,
Is
so.
Yeah. People we like.
Yeah.
Type it.
So these backers is gonna do all of these nights. Where's your like, how do you just turn out? Yeah.
Probably.
Yes, that's what it's at.
Yeah, so we expect I to have like anything to do with it, so.
Yeah, like Swift times, it's like really good. Yeah, stuff like this, generic stuff. Yeah, really nice. Alright, so you've got various generic sounds. What is that?
So it's
On
kind
top
of
of it,
the.
like the varied number of generic.
Yeah.
That can like strongly.
I am doing 3, 4, 5, so that's really
Structure.
So let's take that.
Like for a UI system.
Yeah.
Stack, and then it can take. You know, keep track of what you know.
Well, I think it's.
Yeah, that's cool.
Yeah.
And it has like factory, they call them project office, basically. Yeah, so, I was thinking it'd be cool to try and make an abstract out for a library. Whether it's with like a ring protocol. Yeah, like a field protocol that implies the link protocol. Yes. Like true, so this is the deal. Someone's got a text ring. Yeah. The field. Yeah, that's.
Which is terrible, but that at least helps you doing more of this. Loss. Latte can't.
It is. I wonder, is the type system of Julia? I don't know, but I'm pretty sure function overloading.
Yeah.
Should be true. Yeah, then Swift someone has an example. Where you can set up a new function and you can do function overloading. Okay. And then essentially to solve function
So what do you get?
overloading for this program, the compiler has
Two
to solve
X squared next to.
Boolean satisfiability.
Oh, yeah, two.
So it's like,
Next plus.
yeah, type check.
I think
It's like,
you're reverse printing apart too much. Because it confuses me because I'm used to reading.
I don't know. Yeah, someone made like a. That's what type system.
What about that single logic? Maybe because, yeah.
I think like the results, like outside the confidence.
Yeah.
So. It's great, I love those.
Yeah.
For that.
And then save it as a.
Oh, that
would be interesting seeing like I do have. These these types, the like
first position.
adding this feature, like bringing it from like it's a side or live system, decide easy. And then like.
Yeah,
adding
like that's the good one.
it's like. It's a tool. It's like a bit of a problem, it's not like fun, not about.
Yes, yeah.
Sometimes we have a bunch of expressions, it's two this expression between all the time check, letting it out into small stuff expressions. So it's like everyone who's done it long enough, like, no,
That's working.
like, the function of like all these operators have like 100 different definitions. And they code for it. I'm certain you could do it like.
Okay, so I'm actually trying.
better. That's a little bit. It's quite funny. Or just interesting, like, if you could make a language somewhere like between. It's funny, like, Rust is like getting all these features that are converging towards Swift. Swift is getting all these features that are converging towards Rust.
So it was like.
Like it's getting like ownership and like and stuff. It's like
Isn't that like,
Yeah.
if you only do that once per show?
real performance,
Unless
so
you're doing
you
some
kind
kind
of
of
imitate as far as the distance yet to less.
Yeah.
And then Rust is getting like some sort of features like
Yeah.
Yeah, it's kind of funny.
That's how you go to this project.
I can always go around.
Oh, and don't forget tomorrow at 7, we have another consultation
I
online.
say much harder, but it's not fingers.
Yeah. I mean, make a text edit of it. Shows like.
Yeah. Doesn't look too bad.
Yeah, it is. I did chase. I wrote some flippant response to you,
Like-
like 4 hours is a nothing amount of time. Like I can't.
Oh, it was a lot longer than 4
But-
hours. I just didn't want to
Like-
Yeah, just one spelled up Fortnite looking for a misplaced semi. Right, that was the fault of my supervisor, who just said, oh, you gotta expect these type of things.
Has Max told you about his like single
Oh.
character month long bug?
No.
It's like risk emulator.
Can you put yours again, start from like reset the one kernel?
It was like.
This is the one where you open like you're showing like this is doing.
It was the previous one where it was like. I think there was this one configuration file for how memory is interpreted or something.
Yeah.
And there was a hyphen instead of an underscore. But there was some code inside QEMU that like, it just has a default, so it doesn't tell you. And
Yeah.
it allows custom properties, so it doesn't tell you that's not no. That's, and then it just would like, I find this, like the kernel, like, that's funny, loses that.
Yeah.
Yeah.
No, you can just say,
How do you even like debug?
you just say, oh, yeah, let it pass, that's safer. So he solved
And
it.
actually.
Yeah.
Oh, yeah, well, just to run this.
No, he did, that cyber squad, he did like a tour on
Right.
like, it's that kind of stuff, yeah. A few weeks ago,
Yeah.
I think he's still working on some other issues that.
Yeah. Wants to show me this something. I'm not sure.
Yeah.
Oh, Windows computers are
Try and get like the next running.
Yeah.
I've never seen.
Yeah, that was it. That's, yeah, he's trying to get it. Because they're technically units. It's operating systems. Chinese remanded here. It's like
Fix that.
this PowerShell sort of brings it more compliance with Unix development with PC. That's how everything, all software is developed effectively with Linux.
And
Just weird, Windows had its like timing.
they all actually manually implemented the GC.
But, oh, that's, yeah. Like, we can always saw Julia base, yeah.
The GC is the best. But they've actually re-implemented it using these part of the factory test. Yeah, it's more generalized.
Do you have like a smaller file? Like an example file?
For this.
Yeah. So like what happens if you put this example just to, or if you're doing another one?
Like define this, right? You put down and then in reverse, with the original on rings, and then anything that defines or ring.
Yeah.
Suits the like sort of.
So here you should like an example workers.
Yeah, it would really be good if there was some sort of like place.
Yeah, I was like looking into
So
it,
this,
and
for me, is preferable.
then
Because it really starts from scratch.
when I'm looking into it, I was like, oh, I'm not seeing why. they
Sometimes
did that.
I'm trying
Like, in the dark, they chose,
Yeah,
whatever.
and I've made a change. The changes won't be
Really
reflected
things
in
is that
that section.
yeah,
It's here and
doesn't like
So no,
into like every time checking
Mm,
functions that
that's
are
very
every time. I think that's what I have.
Which like I created like that.
It's, yeah.
So-
Because I was like, nice and clear about
Yeah,
it.
here's your
It's like
example.
an annotated almost function that takes me to Jared.
I'm just gonna put it next.
Or something that is called.
Yeah, which means nothing after this. That's probably one of the biggest problem with it is that he's removing.
People can't annotate. It's
Other
really-
people do that.
Like, you can't just
let's put your
annotate
example.
along with this type of function.
So what was that?
Yeah, like to have function types.
Yeah.
Yeah, it's a bit of a pain.
It's like.
Oh, yeah.
And we've like with code that document.
Yeah.
And same with like not having interfaces. It's kind of annoying, but I see why they. I think as well for the overload resolution to be like. Or like for
Actually,
infection types.
pretty printing and figure out
Like
like
they need like a strict hierarchy. I don't like that like everything is only has like one parent.
Yeah.
It's like. But those aren't.
Yeah.
Any of those.
Push up.
Yeah.
Awesome.
That gets you
Yeah,
much faster, hit enter.
Yeah. I would be interested to see like how much
They look great, so you don't have the
Where
first double
it
digit.
is.
Box and ridiculous.
Yeah. Yeah, it's weird, I like calling it methods. Why is it like, I'm not used to that word, being used in that way. Yeah. And then it's like, yeah,
It is great.
and then it's like. Kind of weird,
There's
like,
no reason not to.
they kind of experience the detail that.
No, it's just gonna go, it's just going to get it.
Have like a defined target, so they
This is a flip and have to
external variables, like, then they kind of, like, you have
Like,
an autonomous function.
yeah,
that
action,
actions,
yes,
and then
it's not too much.
it's not just a pointer to the
Oh,
code, like a pointer to a thing storing the data.
No, I'm like, I was sort of having curiosity.
Yeah.
Stubborn like
Hello?
So, but.
Yeah, I was much rather use this.
Oh.
Yeah, given those are the alternatives.
Yeah, so I'm doing like just my kind of shitty scripting. Like, Julie over.
Oh, yeah.
Python.
Nice.
I use like the type annotation in Python anyway, because it helps me run that.
Yeah, yeah.
You have used 1001?
I did.
Okay, that still lingers, right?
Yeah, so before that, my code had no type annotations.
It's better than what you expect
Yeah.
to come in and come out.
Absolutely. Yeah.
Inch 1001 refused to do it.
Very engineer. This function returns approximately an integer.
Where was that?
Most of the time it returns.
Also mine isn't super.
In like function annotation, like you can annotate a return type, but like stochastic return type, sometimes a string.
It's kind of symbolic with like uncertainty values. Like, whereas it's like uncertainty properties. So you might have like 1 plus minus 2, and then you add 2 plus minus 2, and it's like 3 plus
We don't
minus.
have to run it. It's like
Oh, yeah.
Example script just.
And you just have something that can do that for you,
Oh, true, yeah.
and ideally do it like exactly.
Yeah, that would be good.
That's the fun thing then is what type of distribution is the error? Because if it's a like square function, then it behaves differently with its normal or like something else like couchy. I did one of those.
Likewise.
Oh, which was that?
Yeah, that's why I'm suspect that I think something else must be printing. There's some subroutine that's being in my. At that point, this happens, it's working fine.
Yeah.
You got, it's somehow in one account, swing to box. Yes, you have to go search for where you have shows your plans.
So have you've done,
May have put something somewhere.
you go into the like what you clone the project.
Show me where, so this gets printed in the show.
You go, you git commit and then you get printed and shown.
This whole.
Oh,
Yeah, a bit.
see, I don't know how to switch it, so I want to go abstract.
Maybe it's explanation. You're not away.
generating code from that.
I think like LLVM is very popular for doing that, but if you wanna just like do. Like manually to like learn and stuff, to
Yeah.
get like to assembly.
Yeah, exactly.
I think
Because these monitors are supposed to be immediate.
I'm like been writing an interpreter a while ago, but like I type check the stuff for interpreter, so it's kind of like a bit simpler.
Is it?
And when I'm type checking,
Yeah,
I
like read for the first.
like replace all the names, and I think most compilers, they take AST and turn it into like a sort of like a video representation.
Yeah, there's one.
Where it's all jumps and go-tos.
Yeah.
And then once you've got that.
Yeah, so like, I guess the first thing I put down, including in kind of, it's like, there's like a branch, and sort of things go to the previous.
Yeah.
So they can just very.
Yeah, it's nice. Yeah, and you like, once you've got that, then
Meetings
that's
are
quite easy. It's like
and that is the
information,
important
like,
for them.
more of a straightforward.
Yeah, I guess maybe I should
Trust that contain the process.
So I guess the problem is that it's like, you know, I go down and made my very bad. I struck.
Depending on
I
that,
go down to
then
I
it's one that's strong.
That's the right.
Right,
I guess.
Put it up and then
Yeah.
That's the issue.
That you won't need to send it over.
Yeah. In my like interpreted one, I kind of like,
Like,
everything I have,
that's
an
not.
AST, I go over, it doesn't actually matter, I have a structure.
No, I don't think it doesn't.
Mutate.
That is.
Yes.
And you can like populate that with all the types and functions I come across. I'm an AST type and a type.
And in some languages,
Yeah,
actually,
that two outputs.
it's.
But I couldn't find any
Ownership from functions.
doing it. This copy is all.
So much of
Like,
so much.
it's all-
Like
It has assumption.
like you do, like, like just assume that it's not intended, right?
Yeah, and like it just says someone will have to do it zero. Then the interpreter happens to just go, okay, I'll get some zero run. And then it's run.
Each member schools do my thing.
Oh, you would be wild.
One, yes, it's right down, it's like, I was telling you what this is gonna be about, but not sorry, it's like, where you're getting information rather than like.
Yeah, like loops and branches, literally, properties and stuff.
I usually teach that.
Like,
Yeah.
you kind of just.
I usually teach.
Triple E's.
We just say idle because.
Values by registers or points,
Yeah.
stuff like that. Yeah, right. That's good. Yeah.
And I try to use. We don't know anything as well. So you can set up.
Oh, right. Yeah. Yeah.
Run out of services and possibly all, sorry. It's almost slides on the course, it's actually like that.
Oh, okay, yeah.
Like. Okay, it was fine initially, but you still have the vision and take a part of the see of the. Oh, yeah, I see that
Now, I just want to express interest on one things.
Oh, yes, send me a email, like you export, like you're ready to go
Okay.
in another.
I mean,
Something to.
Yeah.
Arrange the type, I need to use.
But.
Yeah, figure it out, yeah, contact. Or that. Or that I can't use. Pleasure having you
Yeah.
around, and because they're all like. You again, obviously. I'm like using the stack pointer and so much. Yeah.
Yeah. Yeah, like that's probably the one of the hard parts of like making this file.
Yeah.
They're always like shuffling things in and out of like the stack.
Yeah.
And like, most of the time,
Those are coming from.
so I think there's like a big read list of registers that it's like C goes every function before a return to make sure the registers are intact still. And then you can kind of just. Once you know which ones you need to say, you can, if you just want to be naive, just go, okay, push, and then you get pop.
Yeah.
Like every single register you might say.
Yeah.
But yeah, if you're like hand kind of generating.
That's the
I
thing.
mean, you like that, kind of like basically doing some basic stuff with the assembly.
Almost,
Oh, yeah, I think it fully works. It's
That's cool.
Yeah,
you're not telling this to print, it's like, that's the address of the type. So the type are physically sorted there.
Yeah,
And the print, you just, like, there's a keyboard output, but like, right, the SDD out.
There are many places we can print.
It just, I basically, so.
Naturally,
all the
lamps.
lamps.
Yeah, passes the pointer to the right side of the type. To the end.
Like that.
and it just-
Oh, hello. Oh, thank you. Come visit me in the general
The side,
side,
yeah.
and I'll be around tomorrow.
Just like the.
Otherwise, if you're interested, I'll throw you for honors, my
Yeah,
sort of baby in computer science, mathematician, smash it. So free 7 months.
Yeah, okay.
You may enjoy it. It's Pascal programming, the functional paradigm.
That's.
And if you're interested in doing it,
Yeah.
just speak with me, just come on,
Yeah.
or send an email.
And like everything's like equal now.
Yeah, it's
amazing. I don't see like some languages, they kind of like start as well, which would be very kind of. The first iteration is just compiling.
That was a bad
the,
thing.
like.
Yeah,
C
they-
code, like, I think.
I wanna help with something.
That does.
Yeah.
So it's usually
Just
how
ran
they
file
output
C,
the
and then it compiles the C.
Yeah,
The benefit is like
I always
C files are like really fast.
Yeah.
So if you design your language in a way that all your like fancy features can just be like
network.
converted to plain C, so it's like, because if you wanna do like functional loading,
Yeah.
that's gonna be.
Yeah, you got screwed because in Python you don't have
Like you all and file needs to be fast,
Yeah,
and actually like
and the worst part that it still worked.
resolve the overloads before it's
Silent running, there's a very big error,
Yeah.
this is bugs are worse than errors, errors are worse than. So what was happening, yeah, is that it's hard to explain,
Yeah.
because printing is handled by the operating
C,
system. And
which is like weirdly unspecified.
our show gives you
Specified language.
like something has to say, like, no problem,
Yeah.
check the email, update the screen, like ask if the user typed something on the keyboard, it can't actually do all of that stuff simultaneously. So you know, how you like you watch a movie, it's not blue, it's just a bunch of images that are flashed fast enough, so that it gives the appearance of animation. This is the same thing happening. The screen only updates like once every millisecond or something like that, so it does a bunch of stuff in between. So what stuff does it does in between? Well, it's pretty complicated. The computer has a very sophisticated scheduling algorithm. Right, to say I have to do the following things at the following priority, I will do it. So sometimes if your computer is like stuck, it's like has a lot of stuff in its scheduling and it's trying to like solve it all before getting to yours. So one of the things that the computer hates doing is outputting it. Because it takes a long time to output something to the screen. So it usually tries to collect a bunch of stuff to output it and then outputs it at the same time. So what this was happening is that somehow you were putting prints onto this priority stack. These ones of the IO were like going to the front. And then this one in the schedule was like, where does the print? Where should we put that? Oh, its default state is the IO, and then it got stacked too late.
Okay.
And so that's how, like, when I saw what was happening, I'm like, this is a scheduling, this is a race condition. Like, these prints are being put into the scheduler with different priorities. And that's why now that print has the same priority as.
Awesome, I never thought that would make sense.
Yeah, it does make sense once you understand what's happening. Yeah, so the thing about the computer is it's always doing exactly what you've told it to.
That's what I hate, when there's a mistake, it's actually my fault.
Well, yes, yeah, when I was studying with a professor when I was in high school, I was complaining the code wasn't working perfectly. The code is working perfectly, it's doing exactly what you told it to do. And there's a
Yeah.
poem called The Programmer's Lament. That is, how does it go? Oh, yeah. I really hate this damn machine, I wish that I could sell it. It never does quite what I want, just only what I tell it. So then you keep that, but that was a tough button to find. Yeah, you know, this fellow was saying phone numbers, I have to find you because I just misspelled one to something. Well, welcome to the club.
I failed to find polynomial by integer, that was 2 hours of what they use.
Oh, but that is,
I fixed
that's
it,
an
though.
excuse. Yeah, that's the nature of the discipline, like,
Yeah.
it takes 3 times, like, I threw away my entire dissertation. Like thousands of lines of code and restarted. That was a tough day.
But you at least had direction then, like it does, it's clearer in your head where you go.
Yes,
So-
yes. It takes, oh, someone raised their hand. Sorry.
All good.
Is it all right to ask how Sierra or less the ticks?
Yeah, I don't
Well,
really.
Han, are you still around?
Yeah, I'm still here. Hello?
Is that okay? Shoot. Oh, yes.
Thank you
Yeah.
so much.
See you later.
Sorry, Paul, can you not hear Rowan?
Hello?
Sorry, you'll have to type.
Yeah, I can't hear you. Hold on. Let me see. Unplug from everything. Maybe that. You spot talk now?
Hello?
Yeah, I can hear you now. What's up?
Okay. Yeah, no, I didn't really understand task 6 in general. I saw a bit of the unit 6 CRT stuff, but I'm not sure how to actually use that or
Right. Okay. So a big
Mhm.
int on this on a with Julia is more expensive to work with than non-big ints. Does
yeah.
that statement make sense to you?
Yeah, I've seen that firsthand.
Okay, cool. Okay.
Yeah.
So what Chinese remainder theorem allows us to do is solve a problem that requires big ints using only not big ints.
Right.
Right? So we can solve the problem using machine integers and then use Chinese remainder theorem to reconstruct the answers over the entire integers.
I see. And I'm a little lost as to how I actually apply that to the algorithm. I just,
Well, this is specifically for multiplication, right?
yeah.
So multiplication, there's a slide. Pull it up. Did you watch the lecture where I went over this? I'll just pull it up.
I think the second half was no video.
Oh, we re-uploaded that and there is, but I think I only went over this maybe last lecture or the lecture before. Here.
I've been struggling to keep up with the lectures because I've been trying to keep up with all my assignments.
That's no problem. I'll just show you this, because this is what you need right here. Okay.
So you have,
Multiplication by Chinese remainder theorem. You see?
yeah.
Okay, so here's the idea. So I have two polynomials, A and B, and they
Yeah.
multiply out to this.
Yeah.
So I'm saying, okay, look, do the multiplication mod 5, and you'll get 3x squared plus 1x plus 0. And furthermore, you don't require big ints to do this, right? Because the biggest number you'll need is 4. Agree?
Yeah.
We can also solve the problem mod 7, and we can also solve the problem mod 3, right? So here's the product mod 5, mod 7, and mod 3.
Yeah.
Okay, so I'm saying, well, what does this mean? Right? This means that the solution over the integers, right? The leading coefficient of C is 3 mod 5, 4 mod 7, 0 mod 3. And Chinese remainder theorem solves that and says, oh, it's 18, right? The leading coefficient should be 18. Does that make sense?
I think you've lost me there. So
Right. So we do A times B over the integers, and we get 18x squared minus 9x minus 20.
yes.
That's just arithmetic, yeah?
Yes, that makes sense.
Okay. I'm also saying, look, if we needed to do this with big ints, that could be slow.
Yeah.
So what we can do is do the multiplications over smaller residue classes, right? So if you multiplied 3x plus 1 plus x plus 0, you get 3x squared plus 1x plus 0, right? This is the product mod 5. Do you understand that?
That makes sense. Yeah.
This is the product mod 7, and this is the product mod 3.
Yeah.
Okay, so this means, though, that the solution over the integers, right? I know that over the integers, right, the leading coefficient of the actual answer is 3 mod 5, 4 mod 7, and 0 mod 3. What number is 3 mod 5, 4 mod 7, 0 mod 3? This is what Chinese remainder theorem answers.
I see. So we're looking for the leading coefficients for. Wait.
Like, this isn't the answer, like over the integers, but this is the answer over Z5, yeah?
Yeah.
But I want the answers over the integers. Big ints, right?
Yep. So then, what we want is,
Like I'm saying, I can recover the integer answer.
oh wait,
by-
oh, I see, using the Chinese remainder theorem.
Exactly, right? Because the leading coefficient is 3 mod 5, 4 mod 7, 0 mod 3. Chinese remainder theorem says the answer is 18. The leading coefficient is 18. 18 is 3 mod 5, 4 mod 7, 0 mod 3.
I see, and we're doing that for each set of
And
terms.
then we do the same thing for the linear terms, the same thing for the constant terms.
I see. So we want something that sort of iterates through each set of terms.
Well, I actually gave pseudocode for doing this, right? So you
Wait,
don't have to
what?
think that deeply, right?
Oh,
It's where was it? Here, Chinese remainder theorem on two polynomials. There's some
I see.
pseudocode. And then there's the pseudocode for CRT multiplication is here.
Right. So then the pseudocode for CRT, that's A, B, those are the polynomials in integers or the polynomial big?
These are integers. These are polynomials, period, right? With big int coefficients, sure.
Right. And NM. So it says such that A in Zn. Is that just
Like, because like this is going to recombine everything back to like big ints, right? So here, like to combine this one with this one, like you have a polynomial mod 3 and a polynomial mod 7. So
Yeah.
this is going to give you back the answer mod 21, or sorry, answer mod 35,
Yep.
right? And then as soon as you exceed the bound that I gave, this bound,
Right.
this bound,
Two
right? Then
times the
you'll
height
have
of
the
C?
solutions over the integers. Yeah.
Wait, so is the bound 2 times the height of C or?
Technically speaking, but we can't get the height of C because C is the product. So we actually have this sort of less sharp bound. Height of A times height of B times the minimum of the number of non-zero terms of A and B.
Oh, so we want to exceed that.
You should go back and watch like the lecture, like maybe last lecture I talked about this in way more detail. Because
I see.
effectively I'm just repeating what I said in the lecture, just more
Right.
poorly.
I see.
But that's the idea, right? Like we can do mod P calculate, we can work in ZP rather than the big ints, and working ZP is way faster.
Awesome, I see. Okay, I think I understand. Thank you.
So to take a look at that section, take a look at the pseudocode, because you just really need to faithfully implement that pseudocode. And if you're still having trouble, we can sort this out tomorrow.
Tomorrow.
There's a 7 o'clock session where we're going to meet on Zoom and help anyone needs help.
Awesome. Thank you so much.
No problem, no problem. See you tomorrow then, if you'll need it. Good luck until
Good
then.
night.
See you later.